but now I do. And it's very tiring. No, because I'm a professional. Okay, anybody have any homework questions? Yes, on vectors or on matrices? Okay, I don't have that here. Do you have it with you? Okay, matrices number 4. Are you guys talking about matrices? Okay. Okay, so A is 1, 0, 3, negative 5, 5, 2. And B is 4, 1, 3, negative 7, 2, negative 9. And we're supposed to give the sizes of them. Well, okay. So first, the size of A. So the size is the number of rows followed by the number of columns. So A is size 3 by 2. Okay. B only has 2 rows and 3 columns, so B is 2 by 3. And even though, I mean, it's kind of just, it's not really an understanding thing. It's just sort of remembering the protocol for which one you call first. Understanding anything about what's required for multiplying matrices together, lots of other stuff depends on having this kind of in your head, the order. So it has to be rows first, columns second. See the value of A12. So then we're talking about the first row, second column. So that's 0. What's the value of B21? So that's on the matrix B. Second row, first column, so negative 7. And then E, which one can we calculate? Can we calculate A, B, or BA? So multiplying with A on the left and B on the right, or multiplying with B on the right and A on the left. They might both be possible, actually. But so AB would be 1, 0, 3, negative 5, 5, 2, multiplied by 4, 1, 3, negative 7, 2, negative 9. And the way you calculate that is, oops. Remember, these are dot products between the rows of the left matrix and the columns of the right matrix. So they have to be the same length. And here, the length of both of those two are 2. And so this works. So yes, this is possible. What about the other way? So if we have 4, 1, 3, negative 7, 2, negative 9, and then multiplied by 1, 0, 3, negative 5, 5, 2. Dot products here are those rows dotted with these columns. Those aren't the same length as the vectors that we're taking the dot product between in the first case, but they're the same as each other, so you can still do it. So this is also possible. Okay, so yeah, that's the next. So the first one, we have, so in the first case, we have 3 by 2 multiplied by a 2 by 3. Um, and so this has the same number of rows. Well, no, this has 3 rows. This has 3 columns. And so if you multiply those, you're going to get a 3 by 3 matrix. The second one, the left matrix has 2 rows. The right matrix has 2 columns. So this one, just like you said, will give you a 2 by 2 matrix. And this is not an example, but there are cases where you can only multiply. The only reason we can do this both ways is because of the symmetry of these. 2 rows and 3 columns versus 3 rows and 2 columns. But if we made up one that was like, well, let's say we had a matrix 1, 6, 1, and a matrix 2, 0, 1, 1, 1, 2. Okay, well, if we say that this is A and this is B, A times B is not possible, but B times A is possible, and it would give a 2 by 1 matrix. Mostly, that kind of stuff isn't going to come up in this class because the matrices we're going to multiply are mostly 3 by 3 matrices. Any questions about that? Any other homework questions? All right, so now we're going to introduce the stress tensor. And the stress tensor is a measure of load at a single material point. So when we do calculations later on with whole bodies that are set up in structures, we'll often calculate a stress tensor, a strain, but you need to remember that, what we're doing there is just finding the state of stress and strain at a single spot out of infinitely many spots in a body. Okay. Hopefully, when we do this, we have some reason for choosing the point that we're choosing. For some reason, we know that this is the point that we're most concerned is going to start a fracture or something, and then that's the point we look at. But a stress tensor only represents a single point. And not only is it a measure of load at a single material point, but it's the best single measurement. You can put some things together to get better measurements, but if you're looking for a single physical quantity that gives you the best sense of whether you're going to have a fracture start at a point. This is it. Um, so for determining the likelihood of fracture at a point. Okay. Well, in statics, we started talking um, about internal loads. And so really, internal loads was the first glance, first glimpse of trying to figure out how likely an object is to break at a point. Um, if you think about it, this is how I talked about it in statics. I mostly just do this because I'm good at drawing thumbs and stuff this way. But okay, so if you're holding like a pencil, okay, and you're going to do that until it breaks, okay? Um, a free body diagram of the pencil would look something like this. We'd have the thumbs pushing up and the fingers pushing down, okay? And so before you start thinking about internal loads, you look at that free body diagram and say, um, well, there are a few candidates for where this is most likely to break. You're applying forces here, 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 and here. Okay, so those are probably the candidates. But from experience, I guess, or your intuition tells you that if you do this, it's not going to break at any of those 4 points. It's going to break somewhere in between your thumbs, and so you need a new thing besides just external loads. You need a new kind of calculation to predict where it's going to fail. Okay. And the first thing we come up with is so it doesn't break at the external loads. It breaks, and we can't say where in here it's going to break. That just depends on little where you have little weak points or whatever. But it breaks somewhere in that red region. The internal loads are maximum. The internal loads are greatest. But if you think about what you're doing with internal loads, when you calculate the internal loads in a beam, so here's the beam, you're not calculating internal loads at a point. That wasn't super obvious when we talked about internal loads because we didn't really discuss the thickness and we didn't talk about what's happening into the page. But if you're talking about total forces acting at some position along the length of the beam, you're really talking about a total set of loads at some surface of the beam. Okay, so we're really not narrowing it down all the way to differentiating between points on the beam. So internal loads doesn't measure a point. It measures the loads on an entire surface. Okay, so how many points make up this surface? Like 13? More. So we want a way to just go deeper into it and figure out how to differentiate between is a fracture going to start at this point here, or this point here, or this point here? Okay. So that's kind of the starting point. Internal loads tells us something, although it's only useful for long, slender beams. We want to be able to be more general in the kinds of structures that we can look at. We also want more detail than what internal loads tell us. So now we want to investigate the loading at an individual material point. Okay. So let's say this is the beam. And let's choose some small finite cube of material inside this beam. Okay, so this is a finite material cube that's centered at the point we're investigating. So what's the loading on that cube? So I'm going to draw a free body diagram of that cube. How is that loaded? Well, on each face, think about the connection between that cube, which is imaginary because it's just part of the material of the whole thing. So think about the connection between that cube, each face of that cube, and the surrounding material. So in statics, we talked about all the different joint types. What kind of joint is it connecting, say, the front face of this cube with the material surrounding it? Fixed joint? Yeah, right. So we have 6 faces, and each one of those faces makes a fixed joint with its surroundings. Okay, and so if we're going to draw those loads, we have a force vector like that, and then we have components of a couple along every axis. With me on that? Uh, I can only draw 3 of them. There's 6 of them. 3 of them are obscured in this picture. So for this finite cube, how many unknown reaction loads do we have? So each face has 6 loads, 3 forces and 3 couples, right? And we have 6 faces, so that's 36 unknown reactions. Okay, this is finite, so it doesn't exactly represent what's happening at that point. It just represents what's happening around that point, right? It would really tell us more if we, like, the closer we shrink this cube down to the point we're looking at, the more it tells us about what's really happening at that point. You with me on that? So what we really want is like a limit of the loads on this cube as we shrink down, as the sides get closer and closer to the point we're looking at. So there's 36 total reaction loads on this finite cube. Um, to find out the loading at the point, which is at the center of that cube, we want to shrink the cube toward, an infinitesimal size. Okay, so we're starting out with 18 forces, 18 couples, and we want to see what happens as we shrink the cube. Okay. What do you think happens to those forces and those couples if you shrink that cube down to 0? Um, I mean, right now we have, say one of these total forces represents all of the distributed forces acting on this face this big, would sort of make sense if you shrunk it to half that size. That force would get cut in half, roughly, all things else being equal. And so if you shrink those faces down to 0, you're also shrinking down those reactions to 0. Okay. So, and so you lose the ability to find, it doesn't give you any information about the loading. So the problem is, as you shrink the cube to 0 size, the forces and couples also shrink toward 0. So what we're going to do is, you can think of that as like that was our first idea, but it didn't quite work. But we can tweak it a little bit and make it work. So instead, think of those 36 loads as force per area of the face, and couple per area. When I say area, I'm talking about the area of each individual face. if you do that, now you're dividing by this thing that's going to zero. You get one of those things that they talk about in calculus. What are those called? In something, in uh, indeterminate something, form, something like that. Yeah. But they come out, remember, so if you take the limit of something that goes to zero over something that goes to zero, sometimes if it might still go to infinity, it might still go to zero, but if you're lucky, it goes to some finite value. And what we have here is a set of values that go towards a finite value, and now they give us a measure of something. Well, one does. Um, Force per area approaches finite values. Couple per area still goes to zero. So we're just going to ignore these. The force per area is what we're going to use to measure the loading at that point. And this way of approaching it says that the couple per area is not important. Okay. Compared to force per area, this goes away. And it goes away because not only is the force approaching zero, but just sort of loosely speaking, a moment is a force times a distance. And to calculate a moment, you're multiplying a force that's going to zero times a distance that's going to zero. And so it goes to zero extra fast. Okay. Okay. So how many values are we left with now? So now we have 18 values. So after limiting the cube to zero size, the loading at the point is represented by 18 force per area values. Okay, and this is the idea of stress. But we're gonna see that it does. We can throw a bunch of these away because there's a ton of redundancy. But um, these are the stress at the point. Okay, so now let's think about what we can throw away. Um, we don't need 18 though. Um, we require that this cube is in equilibrium. Um, and we're going to do that in two ways. First, we're going to require force equilibrium. And second, we're going to require moment equilibrium. Force equilibrium says that this cube isn't accelerating, the center of the cube isn't accelerating, and the moment equilibrium says that the cube isn't spinning. Okay, so force equilibrium, so the sum of the forces equal to zero, says that uh, the forces on equal and opposite faces are equal and opposite. Okay, so for example, if you have a cube like this, and on one side you have a force going this way and a force component going this way. I guess these are forces per area, but you can think about them as, well, so actually let's write this as force per area. I guess make this force per area too. But the idea is the only way you can have equilibrium is if this is happening on this face, is to have this happening there and this happening there. That's the only way this works. That causes a moment, so we're going to have to deal with that too. Yep. Um, so yes, that causes a moment, and we'll see how to deal with that in a second. Right, exactly. But if you didn't require this to happen, there's no way you could make it not accelerate. So this is required. And now it brings up this second problem. Okay, and then the moment equilibrium. So sum of the moments per area is equal to 0. Requires that their relationships between the loads parallel to the surfaces. Okay, so let me draw this again. So if we had force that way and a force per area that way, we need this and we need this. But now we have a moment, and the only way to negate that moment is to also have a force parallel to that surface like that, and a force parallel to that surface like that. And now the moment is gone. And so now we need like a naming convention for these things. This So naming convention. What? Oh yeah, yeah. Are there? Okay, so now naming convention. So here's our cube that now we're imagining this being infinitesimal. And this cube corresponds to a coordinate system. So here's the x-axis, y-axis, and z-axis. Okay. And we're going to name the faces based on the axis coming out of that face. Okay. So let me draw the negative axes too. There's the negative z-axis. There's the negative x-axis. Here's the negative y-axis. And that means that this is the positive x face, this cube. This is the positive y face. This is the positive z face. And then the faces that are obscured are the negatives. Okay, so there's a negative x face around this corner, a negative y face under there, and a negative z face all the way in the back. Okay. And the components of these forces, force per area, are named with two subscripts. The first one represents the face. And the second one represents the component of the force per area vector. Okay, so now here's this thing that I'm going to call the stress cube. And I'm always going to draw the stress cube with the x-axis that way to the right, y-axis up, z out of the page. And the loading is, so now I'm going to draw the three force per areas on the positive x face. Okay, so I'm going to call this sigma x, okay, because it's the x face and this is the x component. What's this one called? Sigma y and sigma xz. And then on the positive z face, that's sigma z face, z component. This is sigma z face, x component. And this is sigma z y. And then this is sigma yy, yx, and yz. So force equilibrium says we only need to worry about those just to deal with the positive faces. Because once we know the values at the positive faces, we know what the values on the negative faces have to be. Okay? And then the moment equilibrium says that sigma xy has to equal sigma yx, sigma xz has to equal sigma zx, and sigma yz has to equal sigma zy. Okay, so how many independent load values do we have now? 6, actually. So we only worry about the positive faces, so that's 9. And then we say this one, like once we know this one, we know this one. Once we know this one, we know this one. Once we know this one, we know this one. And so the last thing we're going to do is like think of a good way to represent 9 values. You can do a list of 9 values. It turns out that for some mathematical reasons, it's very convenient to write these as a 3 by 3 matrix. And these requirements from the moment equation say that that 3 by 3 matrix has to be symmetric. Okay. So final stress tensor is a symmetric 3 by 3 matrix. We'll call it sigma under squiggle. And the elements are sigma xx, sigma xy, sigma xz. And then because of symmetry, I'm going to call this one sigma xy again. Sigma yy, sigma yz. And then this one's defined by symmetry, xz. This one's defined by symmetry, yz, and then zz. The units for stress are force per area, and that means that SI units for stress are newtons per meter squared, which is pascals. It's like units of pressure, although it's not a pressure. The diagonal elements, so let's break it up into diagonal elements and off diagonal elements. So XX, YY, and ZZ are the diagonal elements. Look at this stress cube, and what do those 3 have in common? XX, YY, and ZZ. The other things don't have in common with them. They're all perpendicular to their face. Yep. And so those are called the normal stresses. So the diagonal elements are called the normal stresses. And the off diagonal elements are called the shear stresses. And just like, remember shear forces when you did internal loads and statics, these are the stresses that would be developed when you cut something with scissors, with shears. You know, you have one, so say there's a piece of paper here, and you go like this, and when those two edges of the different shears rub against each other, they produce those forces in the material that's parallel to the surface. Okay, so that's a shearing force, and what you develop there are those shear stresses. Okay. Anybody have any questions about that? That's a lot of background. The main thing um, that you're going to have to do problems on is you're going to have to do a lot of stuff where you go back and forth between pictures of the stress cube and the stress tensor itself. Okay. So yeah, that kind of problem. Yeah, I mean, if you okay, so let's say your stress tensor is 5, 0, -1, then this would have to be 0. Let's say this is 50, 2, then this would have to be -1, 2, and let's say this is -10. And these are pascals, which are very small values. You would never calculate, you'd never bother calculating stress for anything for an engineering material where the stresses were that small. So let's say these are in megapascals. That's a more reasonable, like, engineering range of values. So draw the stress cube that corresponds to this. The x-axis goes to the right, y-axis up, z-axis out of the page. Okay, so this says the XX stress is +5. The YY stress is +50. The ZZ stress is -10. So that's going to be a vector toward the face. You know, positive values of those normal stresses are going out of the face. So this would have a value of 10. Now, which element of stress is this 0? XY, so there's nothing on the X face in the Y direction, and therefore there's nothing on the Y face in the X direction because of symmetry. The -1, which stress is that? XZ, so, and that's negative, so that would be going this direction with a value of 1. And that has to be equal to the stress on the Z face in the X direction. So there's also a 1 going this way. And then the last one is on the Y face in the Z direction, 2. That's in the positive Z direction. So there's a stress like this with a value of 2 megapascals. And because of symmetry, there has to be on the Z face 2 going in the Y direction. Okay. Yeah, and go back in the other direction too. And pretty much through this whole class, I'm going to keep having you draw these stress cues so you can just sort of beat it into your head, like even after you calculate stuff later on. And then what isn't shown is that on all those negative faces, you have mirror images of all these.
So would that be like a homework question?
Yep. Or I give you the matrix. Yep, that's right. Any other questions? Okay, have a good weekend. Yep.
Bracket are you talking about?